Welcome to Lecture 3 in our series on evolution and strategy. Lecture 3 is on game theory and evolution. So first of all, what is game theory? So game theory is the mathematics of games, and we can use it to understand animal behaviors. Originally, game theory was intended to understand economic behavior, but we can also apply it to our understanding of biology. You may have come across game theory before if you've seen the film A Beautiful Mind, starring Russell Crowe. In it, Russell Crowe is acting as John Nash, a mathematician who won the Nobel Prize for Economics for his work on game theory. So in game theory, these are competitive games where two or more players take an action. And there are various assumptions in these games. The first assumption is that players are self-interested, players behave rationally, and communication or bargaining between players is limited. So why does game theory work in evolutionary biology? John Maynard Smith, who's photographed here, and other scientists pioneered this work and realized that game theory can apply well to evolutionary biology because evolutionary biology meets the previous assumptions. So first of all, players being self-interested. Well, fitness value is payoff. The ability to survive, reproduce, and have offspring that do the same provides payoff. So that's going to meet that assumption. Secondly, players behave rationally. Rational behavior will equate to consistency of success over evolutionary time. If an organism behaves rationally, then we would expect them to pass on those genes for behaving rationally to their offspring. And so they would be propagated over many generations, and we would expect them to spread rational behavior to spread within a population. That is not that an individual organism is thinking about the rationality necessarily of its behavior, but that organisms with a tendency to behave those ways will be more successful in the long term. Finally, it also meets the assumption of communication and bargaining because animals and plants don't tend to talk, and they have limited communication. So the first game theory game that we're going to look at is the prisoner's dilemma. In the prisoner's dilemma, two criminals are captured by the police and interrogated. If one testifies against the other, he gets a deal, which equates to no jail time at all, and the other will get the maximum jail time of 10 years. If both individuals testify, they will both get major charges, which will equate to 2 years for each of them. If neither testify, they both get minor charges and they get 6 months. The criminals can't trust each other, there's no communication, and must make a choice. So it's important to understand here they have no necessary prior relationship, and they don't know at all how the other one is going to act in the scenario. So the question is, for each individual, is it better to testify or to stay quiet? We can summarize this decision-making process in a matrix like this, at a table like this. So here we have prisoner A's decisions to testify or stay quiet, and prisoner B's decision to testify or stay quiet. If prisoner A testifies and prisoner B testifies, as we say, they'll both get 2 years in prison, which would equate to the group getting 4 years total. If prisoner A stays quiet and prisoner B testifies, A will get 10 years, B will get 0, and vice versa if A testifies and B stays quiet. These give us a total of, each of these gives us a total of 10 years for the group, but of course, one prisoner is getting that full sentence and the other is getting 0. The final possibility, of course, is that prisoner A stays quiet and prisoner B stays quiet, in which case they would both serve 6 months, half a year, giving the group amount of prison time 1 year. So we can see from this that the best thing for the group, the best outcome for both, if we look at what the best strategy is for both together, that would be to stay quiet, because the total cost would be 0.5 plus 0.5, a total of 1 year in jail. But if we look at this from the perspective of each individual, the dynamics change. If prisoner A testifies, let's look at whether it's better for prisoner B to testify or keep quiet. In that case, it's a decision between 2 years in prison or 10 years in prison. So clearly, it is better for prisoner B to testify in that scenario. If prisoner A stays quiet, again, it is better for prisoner B to testify. 0 time in jail as opposed to half a year if they stay quiet. So no matter which option prisoner A chooses, it will be better if prisoner B chooses to testify. So what's best for the individual? To testify. It's better result than quiet, no matter what the other individual does. As a result, the best way of playing this game for both prisoners independently is to testify. Here we see a case where individual selection trumps group selection. What is better for the individual will prevail over what is better for the group. And so we have a kind of suboptimal behavior as a result of individual selection. So the prisoner's dilemma can be applied to lots of different scenarios. I recommend you have a look over this cartoon, which is kind of pointing this out. The other day, I was listening to a radio interview with the head of Heathrow Airport, and the interviewer asked the head of Heathrow whether the current situation with the coronavirus meant that the UK should consider the long-term future of flights in and out of the UK, whether they should be reduced in order to help slow down climate change. And the head of the airport responded that while it does make some difference to reduce flights in and out of the UK, doing so would significantly harm the UK economy. Not only that, but the very small amount of difference that the flights in and out of the UK make on a global scale would not be significant enough to kind of move the needle on climate change at all. Okay, it would hardly make any difference unless the other countries in the world are doing it. His point was, well, other countries in the world aren't going to reduce the number of flights that they are permitting, so why should we? This is classic prisoner's dilemma. What is better for the whole group is not necessarily selected for. What is better for the individual at that time can be selected for. This might be why it's very difficult to persuade groups to carry out behaviors such as throwing away their rubbish if they're out in the countryside, or recycling, or doing things to reduce their carbon footprint when they are weighing up individual benefits versus benefits for the whole group. One other place that we can think about this application is in the criminal justice system. So we can actually tie it fairly closely to the initial kind of analogy. In the criminal justice system, if we think about one of the individuals being innocent, we know that innocent individuals are much less likely to admit to a crime, and guilty are more likely to admit to a crime. Okay, that means that the innocent are more likely to receive a negative payoff because they're more likely to stay quiet, while a guilty party is less likely to receive the negative payoff if we have some kind of plea bargaining involved. Plea bargaining favors the guilty at the expense of the innocent, if you look at it as a system overall. Something to consider. So why do we still see reciprocal altruism in nature? And you think back to our previous lecture on blood sharing between vampire bats, right? Bats would share their blood that they had brought back, they had fed upon with their neighbor, even in cases when they weren't related to the neighbor. That seems to completely violate the logic behind individual actions in the prisoner's dilemma. Well, that is because of some of the flaws with prisoner's dilemma when it comes to modeling real-world scenarios. So what are these problems? First problem is that fixed payoffs in nature are rare. It's very unusual to always get the same payoff for the same action. Secondly, variation between individuals, such as their age, their sex, or food availability, will significantly impact optimal strategy. Okay? All of those things will make a significant difference to what is the best approach for an individual. Thirdly, and this may be the one that you've considered with the bats, repeated experiences will impact future decision making. If we run this situation over and over and over again, the memory of what happened in previous situations will make a difference in what we decide in the future. If we repeat the game, we call this the iterated prisoner's dilemma because there are many iterations of it. The situation changes as a result of the repetition of the game. With memory, testify gets punished, and quiet is appreciated and so will tend to be rewarded. But in a system where all individuals stay quiet, cheating is possible and even favored if everybody is nice. So, what actually works in the real world? Axelrod in 1979 ran an iterated prisoner dilemma tournament, an IPD tournament, between various computer programs that were programmed to take part in the prisoner's dilemma in using various strategies. So each strategy was compared against the other. I think before you find out the results of this experiment, it's worth you playing a similar game yourself and exploring this through this wonderful interactive tool by Nikki Case called The Evolution of Trust. I'll include a link below in this video. Go to that link and have a go at the simulation. On the title page, I recommend moving your cursor around it between these individuals. You'll get a really nice little interactivity with your cursor. And then you'll be given a game to play. In this game, you have one choice. In front of you is a machine. If you put a coin in the machine, the other player will get 3 coins and vice versa. You can either choose to cooperate and put in a coin or cheat and not put in a coin. If you put in a coin and the other player does not, that costs you 1 coin. So your score for the round would be -1 and the other player's score would be 3. If you both put in a coin, then your initial cost is -1, but you'll get 3 coins back. Therefore, your profit effectively will be 2 coins. If you don't put any coins in, your profit and your partner, the other player, does, then you will get 3 coins. You'll play this against various computer programs that are employing different strategies. You should try to maximize your profit from the game. Here's the link. Please complete this activity and the questions that I have provided to go with it, and then return to this video. Pause this video now until you have completed the simulation. Okay, I'm going to assume that you have completed the simulation. Now let's talk about Axelrod's results in 1979. Axelrod ran various simulations against one another. Always Testify. That was one of the programs. One of the programs played Always Stay Quiet. One was Grim Trigger, which stays quiet until betrayed and then testifies forever. One was Tit for Tat, which is to start quiet and then do what the opponent did in previous rounds. And there were various other strategies. Each of these particular ways of playing each of these strategies was tested against the others in lots and lots of different iterations. So what were successful strategies? Generally, it was good to be nice. Being quiet at first was favored over testifying. It was generally successful to be retaliatory. Punishment available to prevent being used, effectively saying, okay, not allowing an individual to be kind of walked over. If the other individual is testifying, then you need to switch your strategy to testify effectively. To be forgiving, this is an interesting one, to prevent an endless spite cycle. Well, you testified last time, so I'm going to testify this fine, testify forever. That can cause problems. And to be clear, random selection was not an effective playing strategy. Interestingly, the overall winner was Tit for Tat, but with a component of forgiveness to prevent that endless spite cycle. This also is mathematically correct, but it also makes logical sense, and we see this reflected in the natural world. Even amongst humans, right, we tend to trust strangers unless we have had a negative experience with them. In which case, if somebody has betrayed our trust, we are less likely to be cooperative with them in the future. A form of tit for tat. If we look at this in amongst animals, it can be tricky to isolate specific behaviors that fit these particular patterns because so many different factors are involved in determining whether an organism carries out a particular behavior or not. Dugatin and Alfieri in 1991 observed some potential tit for tat behavior amongst guppies, these small fish. Guppies have a range of different predators, and when a new object or fish enters their environment, they need to find out if they're dangerous or not. So what guppies do is they go in groups to inspect the potential predators. They'll swim up kind of behind and to the side of the predator rather than approaching them from the front, in a kind of to avoid a kind of danger cone where they're more likely to be eaten. And the benefit of this behavior going as a group, so some group protection, but the reason they're doing it as a group is to gain information. Is this a predator? Is this something they need to be wary of, or is it something that they can effectively ignore? Of course, there is also risk in participating in this behavior. Getting close to a predator means that you're more likely to come to harm. Guppies that hold back, those that don't participate in the group, can still benefit by watching their peers and their behavior after they have approached the predator with a reduced risk. So it is possible to cheat. The researchers in this instance held some of the guppies back effectively, preventing them from participating. And when that happened, their peers who had participated the first time seemed to be less willing in the future to go and partake in the group inspection of the predators. So this appears to be a form of tit for tat behavior. The second game we're going to look at is hawk-dove. In hawk-dove, we have two competing organisms, two competing players that are trying to exploit the same resource. And when they encounter one another, they will be competing for that resource. Competition is by displays, that's the dove strategy, or by fighting, which is the hawk strategy. Hawks will always beat doves in competition. The doves in that situation, when a hawk meets a dove, they don't even display. In display versus display, when two doves meet, or fight versus fight, when two hawks meet, they have a 50-50 victory distribution. So what are the payoffs? Well, getting the resource will get you 50 points. Losing the resource will get you 0 points. Losing a fight, say hawk versus hawk, where an individual loses, costs 100 points due to injury. Notice that this is significantly worse than getting a resource is good. And doves do have a cost of display of -10. So a lot less bad thing to happen to them than losing a fight. So let's keep these rules up here for clarity, and let's look at another of these comparison charts. If the first individual is a hawk and the second individual is a hawk, we can see that there is a 50% chance that an individual will get 50 points, but there is also a 50% chance that an individual will lose 100 points. So if we complete this equation, we get -25 points on average. In other words, for a hawk to meet another hawk, okay, and compete by fighting, overall it's bad news for the hawk. If this hawk here, though, instead meets a dove, they will always win the resource, and so will always get the 50 points. There is no risk of injury. So for hawks, it is much better to meet a dove than to meet a hawk. For doves, if they meet a hawk, they get nothing, but they also manage to avoid the risk of injury, and so their score is 0. If they meet a dove, then they will display, and there's a 50-50 chance that they will win the 50 points. However, displaying does have a cost of -10 every time they display, and they will pay that whether they win or lose. Therefore, their average score when meeting another dove would be 15 points. So we can see that for hawks, it's better to meet a dove, and for doves, it's better to meet a dove. So what is the best strategy? Is it better to be, as an individual, a hawk or a dove? Well, let's consider what the opponent, what the other individuals in the area are doing. You see, it depends on the frequency of other strategies within the group. If there are lots of doves in a population, it is better to be a hawk because you will gain 50 points a lot of the time, and 50 points is better than 15. However, if most of the population is acting as hawks, it is better to be a dove than a hawk because 0 is better than -25. Hawks are better than doves when many others are doves, but doves are better than hawks when many others are hawks. Being rare in your strategy is beneficial. We can plot the average payoff fitness against the hawk frequency like so. We can see that when there are no hawks around, doves have an average payoff of 15, but that drops to 0 if every other individual in the population is a hawk. Hawks, a fitness also drops with the number of hawks that are in the population, but it drops more steeply. If there are no hawks in the population, it is very good to be a hawk because you'll have an average payoff fitness of 50. But if the entire population is hawks, then the average fitness payoff will be -25. So what are the implications of this? This means that there is an equilibrium hawk frequency in the middle where these two lines cross. Maybe you can calculate that using some algebra. If we add individuals of either strategy, that will they will lower the fitness relative to the alternative. So, for example, if we have a population that moves towards having more hawks in this direction, that would mean that being a dove is more beneficial than being a hawk, and so we would expect the number of doves in the population to increase, bringing the hawk frequency back down to this equilibrium. If the number of hawks goes down in a population, well, then it becomes more beneficial to act like a hawk, and so we would expect the number of hawks to increase in the population again, bringing it back to this equilibrium hawk frequency. That means that there is no best pure or single strategy. There's what we say no single evolutionarily stable strategy, or ESS. It is not stable to just be doves or just be hawks. So this is different from the prisoner's dilemma. A population of all doves will be very susceptible to invasion by individuals acting as hawks. A population of all hawks would be very susceptible to invasion by doves. This creates a stable polymorphism where we can have two different individual strategies, balancing one another out. This is called stable polymorphism. One thing to note, which I think is particularly interesting here, is the fitness of individuals is lower at this equilibrium point than in an all-dove population. If every individual behaved as a dove, their fitness would be higher than at this equilibrium frequency. But because of the susceptibility to invasion by hawks, that doesn't happen. So individual selection is once again dominating group selection and lowering overall fitness of the group. Selection acts to lower the population's mean fitness. It's kind of surprising because you've probably thought in the past about how natural selection increases the fitness of individuals. Here we've got a case where it is actually lowering it because of these individual to group dynamics. So let's think about an application of this. We can think about sex ratio. Genes determine offspring's sex. So is it better to have offspring that are male or female? Again, that depends on the frequency of the opposite sex within the community. Here we have the number of males along the x-axis. We can see that when there are very few males, there is a very high payoff to being a male, probably because you're going to be able to meet a lot of females and breed with them. But if there are very, very many males, there's lots and lots of males, then it is significantly better to be a female because you're going to have no problem at all in finding a suitable mate. So we reach another of these stable polymorphisms. You probably think of the inheritance of sex as being 50-50 because of the way that X and Y chromosomes work. Different species have got different systems on determining sex ratio amongst their offspring. But the fact that we have a system that creates 50-50 male and female offspring is not a coincidence. Okay, it's not just a factor of that mechanism. The underlying evolutionary principle is that if there are many females around, it would be better to be male, and if there are very many males around, it would be better to female, and that creates this stable polymorphism. Fitness for sex determination strategies is frequency dependent. Here's another example of this involving some grumpy birds. These are Gouldian finches, studied by Coco, Griffith, and Pryke in 2014. They found that red-headed finches, the red-headed males, were more aggressive and tended to get better nesting sites than their black-headed counterparts. But the black-headed finches, which were more passive, were better at looking after their young. Two different strategies that kind of counter one another and balance each other out. The scientists running this experiment predicted a 30-70 ratio based on the hawk-dove model, and this was exactly the ratio that was observed in the wild populations. You've certainly played at some point the game rock, paper, scissors, and it's very easy to answer the question, which is the best option to pick, rock, paper, or scissors, because we know it depends on what our opponent chooses. In this game of rock, paper, lizard, we have a similar thing going on in the natural world, and this is another example of a stable polymorphism. So Sinovo and Lively in 1996 looked at these lizards, and there are three morphs of male lizards. The blue morph, which we're going to kind of refer to as scissors here, these are the monogamous mate guarders. So they only breed with one female, they will guard her, and they can identify and defeat yellow males. So they can spot the yellow males and they can defeat them. However, these blue males can be defeated by orange males. Orange males have lots of testosterone and stamina, and so can defeat blues. They are territorial usurpers. They will go along and they will steal territories and mates from the blue lizards. So these orange, we'll call them rock, beats scissors, blue. Our third group are the yellow males. These yellow males can fool orange males that they are female, and so adopt a sneaker strategy, sneaking up and breeding with the females when the orange one is not paying sufficient attention to them. So yellow beats orange, orange beats blue, and blue, which is able to identify the yellow males, beats yellow. So we have this system here. So the question is, well, which of these was the most successful strategy? And you've probably guessed it, no one is. No single one is. Interestingly, the scientists found that in one breeding cycle, let's say the number of blue lizards were higher, then in the next breeding cycle, there would be more of the orange lizards. The following breeding cycle after that, there would be more yellow lizards proportionally, and then the next year there would be more blue and orange and yellow, following this cycle of which morph of male was more common within the population. Another way of organisms dealing with this game is to adopt a mixed strategy. We've been thinking about hawks acting as a hawk or acting as a dove, but there is another possibility, which is that you sometimes act as a hawk and sometimes act as a dove. We can call this individual hawk-dove, and if hawk-dove operates as a hawk at the frequency of stable equilibrium, then the mixed strategy can invade either a hawk or a dove population. So if this individual acts as a hawk at this value here over and over again, okay, but this frequency, and then acts as a dove the rest of the time, then they could invade either a hawk or dove population. And this would be a stable approach if all individuals acted as hawk-dove at that frequency. So we could end up with either a stable polymorphism or a stable mixed strategy. Do we have any examples of this? Absolutely. So one of the examples of fixation of a mixed strategy is within tadpoles. So tadpoles have phenotypic plasticity. This means that they have different phenotypes that are possible from the same genotype. Which phenotype they adopt depends on their environment and food availability. If there is a lot of food available, individuals take this smaller morph, okay? And if there is little food available, they tend to take this extra large cannibal morph, which can feed on the smaller forms. The morph depends on the environmental cues, and what we find is that the frequency of the morphs can change a little bit based on the environment, but we get this polymorphism occurring. In Daphnia, Daphnias, which are these water fleas, can either develop these armored spikes or not have them, depending on whether there are predators or no predators in the environment. Obviously, each of these strategies has a different advantage, and the frequency of their strategy varies in different populations. So true equilibrium may differ from the best strategy. In the prisoner's dilemma, the best for both individuals together was to be quiet. But optimal strategy for individual entities was to testify. In hawk-dove, best is for all to be doves, but optimal strategy for an individual is dependent on the context and how others are acting. So what can we conclude about game theory and evolution? Game theory can help us to explain animal behaviors and strategies. Fitness depends on the context of the behavior. There often isn't a single best pure strategy that should always be followed, leading instead to either stable polymorphisms or mixed strategies where individuals take on one strategy some of the time and another strategy the rest of the time. Natural selection of individuals often has the consequence of lowering the fitness of the whole population. This is a surprising finding. Analyzing fitness scenarios in detail to explain behavior can be used in many fields that include decisions and choices, such as economics, such as politics, and international politics, and even in personal decision-making. However, while these simplified models can instruct our understanding, the reality is often significantly more complicated, and we should be careful about reaching conclusions which use simplified models, because often in the wild, many more factors are involved in an individual's decision making.